This is a hydrofoil. She is the descendant of a concept more than 75 years old. But because of modern technology, she now has a bright future in the United States Navy. In the age of speed, we need ships that go fast, no matter what the weather, no matter how high the seas. These ships of the future will have small crews, highly skilled in several areas. Their platform must be stable and reliable, versatile and easy to maneuver. This hydrofoil is operating in heavy seas, yet she maintains a constant level. A destroyer, fighting the same conditions, slams and labors. Her speed is slowed by the rough water. Conventional ships, like a destroyer, are hampered by the added resistance from waves and heavy seas. But hydrofoils are ships with wings. Their foils create lift, and once they are foil-borne, they experience little drag from their relatively small foil systems. The idea of hydrofoils is not new. In 1918, the HD4 was tested in Canada by her designers, Alexander Graham Bell and Casey Baldwin. And even earlier, in 1898, Enrico Fornanini had demonstrated a hydrofoil which could make 40 knots. The Navy has been studying hydrofoils since the late 1940s. We've put foils on a variety of craft in our search for speed and stability. But this little ship was the turning point for the Navy's program. Sea Legs showed the advantages of a fully submerged, automatically controlled foil system, the type that appeared most capable of meeting the Navy's requirements. There are two types of foil systems: fully submerged and surface piercing. The fully submerged system puts the lifting surface completely below the water. Because lift on the foil is relatively unaffected by the water surface, the ship requires an automatic control system to maintain flying height. Surface piercing foils have lifting surfaces that penetrate the water. Lift varies in relation to speed and depth of foil submergence. This system is fundamentally stable because it is self-righting and is used extensively on commercial hydrofoils. However, the fully submerged system provides smoother operation and greater flexibility in heavy seas. Another major distinction in hydrofoils is the distribution of foil areas along the hull. The canard arrangement puts most of the load on large foils aft. In the conventional or airplane configuration, most of the load is borne on two foils forward of the center of gravity. A third foil is necessary in both cases for stability and control. Foils are built of high-strength materials to make them rugged but light. They are retracted for protection and to reduce draft when entering a harbor. Hydrofoils operate much the way a plane is flown. The pilot house resembles a large aircraft cockpit with autopilot, instrumentation, right and left seats. The helmsman handles the controls like a pilot, and hydrofoil sailors speak the pilot's language: take off, land, fly. Inputs to the automatic control system are provided by height sensors, gyros, and accelerometers. Continuous readings are fed directly through a computer to the foil system. Hydraulic actuators then position the control surfaces to the desired angle. Actual control of the submerged foil differs with each design. On this ship, the entire foil is moved to change the angle of attack or lift. This is known as incidence control. Moving the surfaces in response to the automatic control system maintains the ship's altitude and stability, even in rough water. A trailing edge flap coupled to an actuation system is used on this hydrofoil. Navy hydrofoils have two types of propulsion systems, one for hull-borne operations, another for foil-borne operations. Marinized gas turbines provide the power required to keep the ship foil-borne. Two types of thrust producers also are used, water jets and propellers. The water jet consists of an inlet water duct, a pump, and jet nozzle. Seawater enters through ducting into the pump and jets out of nozzles onto the stern. Heavily loaded gears and long transmission systems are eliminated, and the number of moving parts is substantially reduced. However, water jets require more power than propellers and are efficient only up to about 40 knots. For higher speeds, specially designed propellers are used. Each thrust producer system has its advantages and disadvantages, and the choice requires careful analysis. Hydrofoils are expected to operate in the open ocean, where they may be subjected to severe storms. While foils may lift a ship above the waves, she is apt to be hull-borne much of the time. The strength of her hull and its sea-keeping qualities, therefore, are of paramount importance. Hulls currently are built of aluminum alloys, which come closest to satisfying requirements of weight, cost, weldability, and resistance to seawater corrosion. Good structural design is imperative when a hydrofoil impacts with waves bigger than her flying height. She also must survive crash landings, in addition to the routine landings she experiences every day. The Navy's 4 operating hydrofoils are capable of 40 knots when foil-borne. High Point was delivered to the Navy in 1963 by the Boeing Company. As the Navy's oldest hydrofoil, she has been modified several times. She is 115 feet long, with a beam of 33 feet, and weighs 120 tons. Foil-borne, High Point is driven by 2 gas turbine engines. The canard configuration puts 70% of the foil-borne load on the afterfoils. Tucumcari was designed and built by the Boeing Company and delivered in 1968. She is 71 feet long, has a 19-foot beam, and a canard configuration. A water jet system driven by a gas turbine engine provides foil-borne propulsion. 120 tons of water a minute, twice her weight, are pumped through this system. Another water jet driven by a diesel gives her hull-borne power. As a result, she has no propellers. During a recent deployment to Europe, Tucumcari displayed hydrofoil capabilities to other NATO nations. She operated with unconventional ships, such as air cushion vehicles, and participated in several fleet exercises. Tucumcari and Flagstaff are gunboats. Both were extensively evaluated during service in Vietnam and are now assigned to the amphibious forces. Flagstaff was designed and built by the Grumman Aerospace Corporation. She is 74 feet long, has a 21-foot beam, and displaces 68 tons. She has a conventional foil configuration utilizing solid cast aluminum foils. The foil-borne prime mover is a gas turbine engine. When hull-borne, she is powered by 2 water jets, each with a diesel engine. Plainview, the Navy's 4th hydrofoil, was built to evaluate the potential of large ocean-going hydrofoils. Designed by Grumman, she was built by the Lockheed Shipbuilding Company. At 212 feet long, 40 feet wide, and 320 tons, she is currently the largest hydrofoil in the world. Plainview has the conventional or airplane foil configuration. Thrust comes from 2 4-bladed propellers made of titanium. the highest speed props now in the Navy. Plainview's Navy crew consists of 20 enlisted men and 4 officers. Skippers of the Navy's hydrofoils are all young naval officers who come to the ships after extended experience at sea. A fully instrumented ship, the Plainview serves several laboratories and research departments. Instrumentation occupies the area aft of the control station. Television recording and monitoring are used to observe strut and foil areas. Civilians from the research and development community are a constant part of the scene on both Plainview and High Point. Close support comes from the commanding officer of the Special Trials Unit. Potentially, Navy hydrofoils can be used to operate offensively against surface combatants. They can conduct surveillance, patrol, and blockade operations in coastal areas and can mount many of the same weapons carried by much larger ships. Successful trials include using a 152-millimeter gun to hit and destroy targets, or firing torpedoes while cruising at speeds up to 36 knots. Because they fly above the water, they are less vulnerable to underwater explosions than any other craft. The ability to tow a submerged body could be used for underwater anti-submarine warfare systems or for mine-sweeping operations to clear a field of its explosive threat. Depth finders on the foils can sound harbors quickly to see if other ships can enter. Refueling operations can be accomplished 2 ways, by the conventional alongside method or by sending a hose aloft to a helicopter hovering overhead.